Hello students, I'm Dr. Ravindranath Rajotia, teaching you a course on circuits and systems. In the today's lecture, we will see some of the most important Laplace transform pair. I've taken the reference from Theory and Problems of Signals and Systems by Sham, that is the Sham series book. So let's start with them. So we start with the first one. We know the Laplace of an impulse function. So this is an impulse function. The Laplace of an impulse function is equal to 1. That is Laplace of del of t is equal to 1. And its ROC is the entire S-plane. The second one is the unit step function. Unit step function. The Laplace of a unit step function is 1 by s. That is Laplace of u of t is equal to 1 over s. And its ROC is given for all the real values of s which are greater than 0. So this is the ROC. Then we found out the Laplace of a minus of u minus t. U of minus t is on the negative side, and you have a minus of, that is the downside. So also the Laplace of minus of u of minus t is equal to 1 by s. See the difference. So in both the cases, you get Laplace is equal to 1 by s. Let me clearly write this second one. So what do you see from both of them? That the Laplace of ut and Laplace of minus u of minus t are both 1 by s. The difference is that when you found out the ROC, in this case, the ROC exists only if the real part of s is greater than 0. But in the second case, as you can see, the ROC exists for real value of s less than 0. So thus, I think even though the excess may exist or may be same as in this case, but their ROCs are totally different. For a unit ramp function, I can also write this as a ramp of t. And I know how the ramp takes. The ramps takes on the values like this. So if this is the t, and for this positive side, so this will be t into u of t. So therefore, the ramp, either you can write r of t, ramp signal. So this is nothing but a ramp signal, which is also is equal to t into ut. So the Laplace of a ramp, that is t into ut, that is same as Laplace of t dot u of t is equal to 1 by s square. And the ROC is for all the real values of s greater than 0. Then for any power of the ramp, that is t power of k times of ut, the Laplace is equal to factorial k, that is the power of t, k factorial divided by s power of k plus 1. So if you try to relate this with this one, so just observe it very carefully. Here you have t raised to the power of 1. So you have 1 factorial 1 divided by s power of k plus 1. S, that is power is equal to 1. So 1 plus 1 is equal to 2. So in general for any ramp, you have the Laplace of, that is in general. So if you generalize it, this is general formula. In general, the Laplace of t power of k for a unit step positive sided, one-sided function. So this is equal to factorial k, whatever is the power of t, factorial k divided by s power of k plus 1. for which the ROC is S, real part of S greater than 0. Then for e power of minus at, the Laplace is equal to 1 by S plus A. So you can generalize it as the Laplace of e power of minus plus A into ut is equal to, you know that e power of minus at is 1 by S plus A, and for e power of plus at it will be S minus A. So I can generalize this as equal to 1 over S plus A for the case when it is minus 1 minus A, and minus when it is the case for plus. So this is the generalized formula, and you can see the how the ROC will change. For the case minus e power of minus at u of minus t, again you get Laplace as equal to 1 by S plus A, but see the difference between how the ROCs are calculated. It is a similar way as you did with the ut. So in this case, the real part of the S is less than negative of real part of A. Then we come to the next one, t e power of at. You know what is t into ut? You found it that's equal to 1 by S power of k plus 1. Now if it is also multiplied by e power of minus at, the Laplace will be equal to 1 over S plus A square, and the ROC is real part of S is greater than the negative of the real part of A. Similarly, if you go with the negative side of it, then minus of t e power of minus at u of minus t on the left sided, and the negative side, the Laplace is equal to 1 over S plus A whole square, but the ROC is for real part of S less than negative of real part of A. Then you see the Laplace of the sine and the cosine functions. The Laplace of the cosine function is equal to S over S square plus omega square, and the Laplace of the sine of a function is omega oblique S square plus omega square for real part of S greater than 0 for calculating the ROC. Then if the same sines and the cosines are also multiplied by the e power of minus at, then in those cases the Laplace will be equal to, for the cosine, S plus A. As in the case of a simple cosine function, it was S over S square plus omega square. If you multiply it by e power of minus at, so Laplace will be S plus A, and downside also you get S plus A whole square plus omega square. And the last one is e power of minus at multiplied by the sine of the function. In that case, the omega 0 upon S plus A whole square plus omega square. These formulas must be learned by heart, because the applications, when we come to the unit 2, where we find the application of the Laplace in the electrical engineering for the electrical circuits, you will be given the signal in the time domain, and you may be asked to find out the S-plane or the Laplace of that particular signal. So you can directly, given these signals, you can directly substitute the answers as this, and also say what is the ROC. At times you also would require to find out the inverse of the Laplace. Given the signal in the Laplace, you may be asked to find out what is its time domain equivalent. So wherever, that means when you will be saying in the subsequent classes, that when you have the equations in the given Laplace domain of this nature that you see here in the center column, you can directly substitute the counterpart in the time domain. For example, if the S domain equation is 1 over S plus A, you can directly write the answer as equal to e power of minus 80 ut as the answer. And if e power of minus 80 ut is given as the time signal, you can find out by directly substituting the S-plane domain equation as this. So for each and every of these formulas, these exist in a pair. We call them as the transform pair. So given one, you can directly substitute the second one. Given the other, you can write the answer in the time domain. And this will simplify easily using less time without any efforts. So only requirement is that you learn all these formulas by heart so that whenever you see anywhere, wait a minute, let me. So that's all in this lecture. Just take a note of all these formulas, and they will be very useful in the subsequent classes when we go with the practical applications of the Laplace in solving the electrical engineering problems. So you can take a snapshot of it or copy them, write them in your notebook so that in the next classes we are able to make use of them easily. Thank you for watching this lecture.